Hi there, welcome back to this channel. Now in this video we are going to be talking about the photoelectric effect, and it's going to be quite a quick video. We are going to hopefully be solving questions, of course, under this series. We have already covered it in our 5 days of physics, but we're going to discuss further in this video. All right, and if you have not already, please do well to subscribe to the channel. It doesn't cost anything. Just go down, look at the red button below and click it, and of course click the bell notification so that whenever I drop a new video you can be notified. All right, and of course if you have any question based on any O-level, any college physics question that you have, you can, or any topic that is bothering you under college physics that you want me to address, you can always put that topic in the comment section and I will answer you, I promise you. Okay, now let's go. We have photoelectric effect. Now, what is photoelectric effect? Now, it turned out that, even from the name, you see that we have photo and electricity. So that is generation of electricity using what? Photons of light or sunlight, basically. Is that okay? Now, it turns out that if you irradiate a metal plate with a particular frequency of light, it is going to begin to eject electrons. Electrons will begin to pop out of the surface of that, move out of the surface of that metal. Now, this idea was basically found out in 1887. In 1887, by a certain Gustav Hertz. So, and primarily in the same year, he actually worked with a particular Frank, and so they called the experiment was called the Frank-Hertz experiment. Is that okay? So, but he's primarily the one that is attributed to the discovery of electricity, basically. Is that okay? So he found out that a polished metal plate, now that the metal plate had to be polished, so take note of the word I am putting down. A polished metal plate. So what that means is that the physical condition of the metal plate mattered. Is that okay? So a polished metal plate, if irradiated, or when irradiated, emitted electrons. It emitted electrons. So number one, I said the metal plate had to be polished because the physical conditions, such as the smoothness, the orientation of the metal and all of that, relative to the light, mattered or determined how the electrons, if electrons at all will be, if electrons will be ejected at all. All right. So now we know that when you irradiate a polished metal plate with a particular frequency of light, it emits metal plate, it emits electron. Now, you see, why do we study photoelectricity? It is one fundamental aspect of physics that proves the wave-particle duality, of light. Is that okay? Of light. Yeah, first of light, then of matter. Is that okay? So the emission of the photoelectric effect proves the particle wave duality of matter, and this is the way it is, or this is how it does so. Now, if it was only in classical mechanics idea of light that were true, which was according to or as proposed by Eugene or Hughes. Is that okay? That's the way it is pronounced. Now, Eugene, if it was his idea of diffraction of light, he proved that using diffraction of light. And so for a long time, the particle nature of matter, which was first proposed by Sir Isaac Newton, was the first to propose the particulate nature of matter in the 16th century. And when he did that, the particulate nature of light rather, and when he did that, he mentioned the fact that light traveled in small packets. But by the time in the 17th century, I think, Eugene used diffraction to disprove his idea. Diffraction, which was the bending of light, and he mentioned the fact that if light were to travel in particles, in packets of light, it will not be able to diffract. Is that okay? It's not be able to diffract. So if I show, if this was a light source now, and I shine it through this open slit, now this place should not be irradiated. This place should not be lit at all. So for light to appear here, it means that the light bends. So which means that light is not a particle, according to Hughes. Is that okay? Or Eugene? Is that okay? Now, so he disproved the idea. So, and if that idea was actually true, if the idea of light being a wave alone was the only true hypothesis, was the only true theory of through description of the behavior of light, then it means that in photoelectric effect, it means that the higher the intensity of light, or the higher the brightness of the light that is shown on the metal plate, then the higher the electrons that should be emitted. However, it was found out that that was not the case. That the amount of the brightness of the light that was irradiated on the metal plate did not translate to more electrons being ejected. I repeat that they found out that it is not the higher the intensity of light that you shine on the metal plate that will determine that will determine the amount of electrons that will be ejected by the metal plate. So, which therefore disproved the wave theory of light. It's now happened. It was found out, especially by Albert Einstein, who now revived the particulate or particle theory of light. Albert Einstein in 1905, which was when he also propounded the theory of relativity. So in 1905, he was able to revive that theory between 1904 to 1905 of the particulate nature of matter. And how he did that was that he found out that the light, the number of electrons that was ejected depended on the frequency, and not just any frequency. That he found out that there was an amount of frequency at which light will be irradiated for electrons to be ejected, or there is a particular frequency of light that caused an emission of electrons from a metal surface. So it means that not all frequencies led to the what? Led to the emission of electrons. So in that way, he was able to prove that, therefore, that light travels in small small packets called quanta. This was what he called it. So now he called it quanta, and now we know them as photons. Is that okay? So those are small packets of energy. So that was how, and they are massless. Is that okay? Massless packets of energy in which light travel. Is that okay? So it was those. So these massless particles carried a particular amount of energy, which was dependent on the frequency of that photon. Is that okay? So that photon carried an amount of energy which was directly proportional to the frequency of that photon of light. Is that okay? So that frequency was the frequency that was enough or greater than the minimum frequency for the ejection of electrons from a metal surface. That amount of energy that it carried had the frequency or the amount of energy that photon carried. Or photon is basically the amount of energy. Is that okay? Photon is the small packet of energy in which light travels. So which proves the particular nature of matter, so of light. So that amount of energy had, depending on the frequency of light, which will be greater than a particular amount of frequency for the ejection of electrons at all. So it means that for a polished metal plate like this now, electrons are locked into the metal plate. Now for this metal plate to be ejected out of this electron, first, for them to just escape this metal surface, for these electrons, I repeat, to just escape this metal plate, for these electrons, I repeat, to just escape this metal plate, they required to get an amount of energy. Is that okay? So it's just like you want to in a toll booth, for example, there's an amount that you must pay for you to be allowed to pass. So there's an amount of energy that these guys needed, a particular amount of energy that these guys needed for them to be ejected. So if you don't have that amount of energy, electrons will not be ejected. The same way, there's a frequency of light which carries energy in photons. Does that make sense now? There's a frequency of light that needed to a minimum frequency that these guys needed to get so that they'll get the minimum amount of energy needed to escape this metal surface. So by the time they escape this metal surface, if they got more energy from that photon, then they would now move out of the metal. But first, they will escape this metal and maybe lie here. Does that make sense? So maybe they've gained an amount of energy, a minimum amount of energy. They will gain it and they will lie here. And if peradventure the photon gave them more energy than that minimum energy, then they were free to move. So now let's now define terms. So there is a term known as the threshold frequency. It is given as F naught. So this threshold frequency is the minimum frequency that these electrons required to just escape the metal surface. This threshold frequency, you remember that I said that the energy that a photon gains is proportional to the frequency, and not just any frequency. But first, the threshold frequency, because it was found out that if we plotted a graph of the energy against the frequency, it was found out that the higher the frequency, if you shine a particular frequency of light that is not equal to the threshold frequency yet, that there will be no energy gained by the electron, so no movement or no ejection of electron. It now turned out that after a while, where we have gotten to F naught, is that okay? So it means that from here to here, were lower frequency of light that were shown on that metal surface. So we found out that there's a particular amount of frequency, which is this threshold frequency, after which then there is ejection of electrons. There's ejection of electrons. Okay, so now at this point here, there is no ejection of electrons. So you see that it is at this point that there is ejection of electrons. So this minimum frequency that those electrons needed to just come out of the surface of this metal plates is the threshold frequency. So now the minimum energy that they now gained, at this point here is called, so we have defined this, the minimum energy they gain is called the work function. Work function W or phi. So phi is the classical letter, what we use to denote it. Is that okay? Okay. So the work function was the minimum energy required for them to just come out of the metal surface. Those are the electrons. The minimum energy the electrons required to just escape the metal surface. That is what? The work function. So we say that work function is direct proportional to the minimum frequency, which is the threshold frequency. So there's a constant of proportionality here. Phi is going to be equal to what? Hs of naught. Albert Einstein in 1905 discovered that this Max Planck, this H is named Planck's constant. So Albert Einstein found out that Planck's constant had a role to play in this equation. Planck had already studied blackbody radiations before then, and he discovered that there was a particular constant for black bodies. Now, this Planck's constant is exactly equal to 6.63 times 10 to the power minus 34 joules seconds. That's the unit. I could show you how the unit was generated, and that's simple. But basically, this work function is the minimum energy required for the electrons to just escape a metal surface. And the work function of a metal differs from that of another metal. So work function depends on the kind of metal. Is that okay? And of course, also depend on how polished, or that is the smoothness of the metal surface, how polished the metal surface is, and the orientation when it's being radiated, and all of those things. Does that make sense now? So we said that this work function is the minimum energy required for this guy to escape the metal surface. Okay. Now, if that be the case, therefore, when the energy begins to increase as frequency increases, the energy begins to increase as frequency increases, it means that the more energy supplied is used by the electrons to now what? To move. The other energy, the electrons are now escaped at this point, right? So the remaining energy supplied to it is now the energy for what? For kinetic energy, for movement. So from here to here, it gains what? Kinetic energy. The energy for the electrons to move. Okay, I'm going to show you how we measure this. But the case is this. So the total energy that is supplied into the system, is going to be the kinetic energy with which the electrons move plus the work function. Because the work function is the minimum energy supplied to first escape the metal surface, then kinetic energy is the energy with which it moves. So the total energy supplied into the system for the electrons, the total energy of the electron is going to be what? Ke, which is the kinetic energy of the guys, plus what? E plus phi rather. Does that make sense? Okay. Now, so it therefore means that from here, you know that, let's say this is equation 1. So phi will be equal to recall that f sub naught, remember that frequency is v over lambda, and in this case our v is speed of light, so it becomes what? C over lambda. Now this lambda is the particular wavelength of light. That is why it was monochromatic light that Planck found out could be used, so that for exact emission, for emission of electrons to actually occur, use monochromatic light of a particular specific wavelength. Monochromatic means one color spectrum. That one color of the color spectrum. So by the time we introduce it into the equation, phi becomes f naught has now become this. So that is C over lambda naught. So where lambda naught is called the threshold wavelength. Threshold wavelength, which is the minimum wavelength required for the emission of electrons from a metal surface. Okay. Now, before I further derive equations, let me quickly show you how the kinetic energy of the electrons was determined. How is the kinetic energy of the electron determined? So what was done is this. So we have a polished metal plate here and another metal plate here. So then both are in a tube. Now the reason why they are in a tube is to prevent collision with other things in order not to lose energy. If the electrons were exposed here, after irradiation, the electrons will be emitted, we know, but the electrons, if they were not in an enclosed chamber, they will bump into other things and then will lose energy. So they had to be in a vacuum. Is that okay? In a vacuum, so that once they get ejected, they move to that plate. And then when the electrons begin to move, that's what? Current. Now, how did they measure the kinetic energy of the system? So it turns out that once you irradiate with a particular wavelength of light, it's going to begin to, or frequency of light, it's going to begin to, electrons will be ejected here and begin to move here, which is current. Conventional current flows in this direction, but electrons move in that direction. Does that make sense now? Okay. So that is the case for this. So in order to now measure the kinetic energy that these guys got, first, they already know that the kinetic energy that they got, that this energy is equal to the kinetic energy that they got to move from here to here, plus the work function of escaping this plate. So they have known the work function of escaping this plate. So what they now did was to now connect. Now, you know, if electrons are moving from here to here, from this plate to this plate, it means that this guy here is the negative plate. Does that make sense? and this guy is the positive plate. Does that make sense? So if they wanted the electrons to really actually move through here and in through the battery, what they will naturally do is that they should connect a positive plate here and the negative plate here, so that it will be moving from negative to positive, positive to negative. Does that make sense? Does that make sense now? No, electrons are moving from here to here. So it means that, and so current is about, yeah, so electrons are supposed to move in this direction, but electrons are supposed to move, no, this is positive, sorry. This is the positive plate, and this is the negative plate. Electrons move, current moves from positive to negative. Is that okay? Yes, so this is correct. So electrons are supposed to be moving from here. Electrons are moving from here to here. Now, if you connect a battery and you wanted this system to just continue like that, what you should normally do is that this positive should be connected to positive and this negative to negative, so that current will be moving like this. Does that make sense? Current will be moving positive here to negative here. It's not hard, it's not confusing, it's not hard, just listen. So current should be, electrons are going to be ejected from here to here. So which means if electrons are moving like this, then conventional current is flowing like this. So this positive to negative, positive to negative. So this is the normal connection that should happen. But the connection that the scientists made was that they were going to connect the negative to this end and create a concept known as a stopping potential. Because, of course, with this connection, what they are trying to do is that they want to hinder the flow of electrons. So the stopping potential, known as V sub S, now is the amount of potential energy that is just equal to the kinetic energy of the fastest electron in this, that is being emitted in this, from this surface. Now look at this connection vividly. Now positive is connected here, negative is connected here. If electrons were moving here, okay, no, let's eyeball this. Look at this connection here. Electrons will move from here to here. Current should flow from here like this, isn't it? While electrons should move from here downwards, right? Electrons should move from here to this place, while current should flow from here to this place. So if that is the case, electrons are moving in this direction. If electrons are moving in this direction, let's now come back to this. Electrons want to move from in this direction to this next place. Here, electrons want to go from here because it's the irradiated plate. This is the irradiated plate. Electrons want to move from here to this place, whereas electrons are also coming from here. So it means that electrons will be bumping into each other, which means that they want to stop the movement of electrons in the other direction. So what scientists do is that they will increase this voltage up until a level where there is no longer electrons trying to move from here to here, because they have increased the voltage to a level where electrons, there's a maximum amount of electrons that want to move here and is able to stop all the electrons that is coming from here to get from getting to the other plate. Does that make sense? That is, the voltage is high enough to hinder even the fastest electron to move from here to here. So at that point, we have the stopping potential, which is the amount of voltage needed to hinder the fastest electron. So recall that voltage is work done per charge, okay? So, or energy per unit charge, energy supplied per unit charge. So which energy are we talking about here? It's going to be the kinetic energy, because that's what we want to measure, right? So V sub S, because what? The kinetic energy per charge. Now this charge here are electrons, basically. Does that make sense? So if that makes sense, then we have that. By the time of cross multiply, Ke is going to be what? EV sub S. Capital letter V because it's voltage. So remember that K is what? Half mv squared. This is equal to what? EV sub S. So in this case, the stopping potential V sub S is going to be what? mv squared over 2e. Okay? If that be the case, let's call this equation 3. This will be equation 2. No, equation 3. Let's call this equation 4. We'll still modify this equation. So by the time you have that, okay, so for that, let's leave it unnumbered yet. Let's call this equation 3. So by the time you have this, then you know that by the time you have this, by the time you want to make V subject, you know the velocity of the electrons that are moving, the highest velocity, with which the fastest traveling electron is moving. You have that V squared is equal to 2eV sub s over m. So you take square root of both sides, then V will be equal to what? Square root of 2eV sub s over m. Okay, let's call this equation 4. All right, so that is what stopping potential is basically. Now, if that is the case, then we know that E here, recall that we have said that E, the total energy that is given to the electron, is equal to the kinetic energy with which they move plus the minimum energy required to come out of the metal plate. Okay, if that be the case, then E equal to what is kinetic energy? Half mv squared, which is equal to what? What is the stopping this guy phi, which is work function, plus work function is hf naught, so hf sub naught. This will be equation 5, this will be equation 6. Okay, if that be the case, then we solve that E will be equal to half mv squared plus hf naught is that, so I mean phi is also that from what we have calculated or derived, so hc lambda sub naught. Okay, then we also have that if kinetic energy is equal to charge times stopping potential, then E will be equal to what? EV sub s plus hc over lambda. These are all the equations that you can use in calculation. All right, let's get into solving some questions and see that this is actually the case. Okay, now there's something else here that I probably didn't show you in this graph. So in order to get the minimum energy required to escape the metal plate, if we trace this guy down, if we trace this graph down, then at a point here we're going to have a negative work function. So all of this face here is the work function. Is that okay? So it means that the total energy here, or basically the kinetic energy here, is going to be this kinetic energy is going to be the total energy minus or plus negative work function. Does that make sense? And that makes sense by the time you maneuver your equation. Is that okay? So that is that about that. Now let's solve some questions involving this. All right, let's solve the following question. The first one says cesium has a work function of 3 times 10 to the power minus 19 joules. The work function of cesium is, okay, cesium, that's C, is this, 3 times 10 to the power minus 19. And the maximum energy of liberated electrons. So what's the maximum energy? E max of liberated electrons, which is illuminated by light, or frequency that. The frequency of light is 6.7 by 10 to the 14 hertz. Okay, is what? Okay, H is given as 6.6 times 10 to the power minus 35 joules second. I guess that's a mistake, but let's just use what is given. Okay, if this is the case, just recall that the energy that an electron gains is directly proportional to the what? To the frequency. So E will be equal to what? HF. Does that make sense now? This is not threshold frequency now, or the total energy that the system gains is going to be directly proportional to the frequency of the light. Okay? So, and it is said that it has a work function, this guy. Okay? So it now says the maximum energy of the liberated electrons. So if that be the case, in this case we are looking for E and we have H. but we don't have the frequency of the electrons. Okay, we have been given the work function. Okay, so what are we to find? Let's find, okay, we have the frequency, I'm sorry, we have the frequency, and we have Emax. Okay, so it therefore means that, we don't have Emax rather. So it therefore means that the Emax is going to be the work function of the metal plus the kinetic energy. The kinetic energy. Okay? So we have that Emax is going to be the work function plus Ke. Okay, so the Emax in this case is going to be, now what now? The maximum energy of the liberated electrons when it is illuminated by light is going to be first, we don't even know the kinetic energy. Is that okay? So I'm guessing it's the kinetic energy that we're supposed to calculate for. So if that's the case, then we have that Ke will be equal to Emax. Now Emax here is HF. Is that okay? So HF minus work function. So Ke equal to H, which is 6.6 times 10 to the power minus 35 times frequency, which is 6.7 times 10 to the power 14 minus 5, which is 3 times 10 to the power minus 19. Okay, if that be the case, then we have that 6.6 times 6.7. That's going to give us 6.6 times 6.7. So we have 2, 4, 6, 36, 40, 6, 7, so 2, 0, 4. So we have 2, 2, 4, 4, 4. So 4, 4, 2, 2. So we have 4.22 times 10 raised to the power. Now, here we have minus 35 plus 14. Minus 35 plus 14. So, then minus 3 times 10 raised to the power minus 19. So if that be the case, then we have 44.22 times 10 raised to the power. This minus this, 35 and 14, that is 21. Okay, so we have minus 21. So I'm guessing this is supposed to be 4 because that's a constant. It's supposed to be 4. Okay, all right. So, well, the textbook that I got the question from used the 35. Or I wrote, maybe it was my own mistake anyway. So that if this is 34, this would be 20. Is that okay? So that by the time we move, so minus 3 times 10 to the power minus 19. So that by the time we move the 0, the point here, we have 4.422 or 42 times 10 to the power. By the time we move it once, it will be times 10 to the power minus 20 times 10 to the power 1. Is that okay? So this will subtract this. And then we'll have 4.42 times 10 to the power minus 19 minus 3 times 10 to the power minus 19. Okay. So if that's the case, we have 4.42 minus 3.00. So we have 1.42. So the answer is going to be equal to 1.42 times 10 to the power. The reason why I subtracted them directly is because they are multiplying, they have the same factor. Is that okay? So So, or they have like terms, kind of. Is that okay? It's the same factor. Is that okay? That we factorize that out. By the time I solve this is going to become 4.42 minus 3 all times 10 to the power minus 19, which is common to both of them. Is that okay? So we are going to have 1.42 times 10 to the power minus 19 joules. So that's going to be the answer to that. Okay? Now the next one is also another long calculation. Let's solve number 3. Number 3 says the number of photoelectrons emitted from a metal surface depends on the dash. A. Intensity of the radiation. B. Nature of metal surface. And source of radiation. So source of radiation is wrong. Duration of exposure to light. That down doesn't make sense. Is that okay? So the possible answers are between intensity of radiation and nature of the metal surface. Now, take note of the number of photoelectrons. If it were the kinetic energy, answer would be. Now, you remember I said that the intensity of light did not translate to more energy for the electrons to move out. The intensity of light did not translate to more energy. So if that's the case, but the number of photons, once the frequency has been reached, the threshold frequency has been reached, and then the intensity of light, the higher the intensity from that place upward, increase the number of photoelectrons that were ejected. So the answer is going to be intensity of radiation, not the nature of the metal plates. The nature of metal plates only controls if there will be ejection of electrons at all, or how easily the electrons will be ejected. Is that okay? So the nature of metal surface is a very confusing question, though, but the answer is intensity of radiation because it is number of photoelectrons. Maybe it was the kinetic energy. It will only depend on frequency. Is that okay? You know, I mentioned that it will only depend on the frequency of light. That's the kinetic energy. Okay. Let's solve that calculation. So the question says that the kinetic energy of photoelectrons emitted by UV light is of wavelength 1.0 times 10 to the power minus 17 meters. From the surface of aluminum is that. So the kinetic energy is 1.34 times 10 to the power minus 18 joules. Determine the energy of the photons of the UV light. So determine the energy of the photons of the UV light. Recall that the energy is given by HF, right? Okay. So and we are given H. H is this. So and we are given F. We are not given F. Okay, since we are not given F, we can say that E is also equal to what? HC over lambda. Because this is F is V over lambda, or C in this case because speed of light. Okay, so we have E will be equal to H, which is 6.6 times 10 to the power minus 34 times so this is 34 times C, which is 3 times 10 to the power 8 over lambda, which is 1 times 10 to the power minus 7. Okay, so from here 3 times 6.6, that would give us 19.8 times 10 to the power minus 34 plus 8 all over 1 times 10 to the power, this is minus 17, sorry, minus 7. Minus 7. So this over 1 becomes 19.8 times 10 to the power minus 34 plus 8 is going to be minus 26. 4 plus 4. So minus 26 minus 7. I hope that is clear. So we have 1.98 times 10 to the power 1. I'll move the point here. Then times 10 to the power minus 26 plus 7. So this becomes 1.98 times 10 to the power 1 plus this will become 8. 8 minus this will give you 18. Minus 18. Minus 18. What are we looking for? Energy, joules. And that's going to be the answer. All right. Okay, B part says that the work function of the aluminum. Now, the work function of the aluminum, we are given that so we are looking for work function. Okay, so we have been given that. Okay, we know that E is equal to KE plus the work function. So work function will be equal to E minus KE. Is that okay? And E is this, so work function is equal to 1.98 times 10 to the power minus 18 minus KE. KE, the KE is given as this, 1.34 times 10 to the power minus 18. 1.34 times 10 to the power minus 18. So by the time you subtract, work function will be equal to, you factor out this 10 raised to the power minus 18 that they have in common into bracket 1.98 minus 1.34. Okay, so 1.98 minus 1.34, 0.64. So we have 0.64 times 10 to the power minus 18. By the time I bring this guy forward, it becomes 6.4 times 10 to the power minus 1 minus 18. That becomes minus 19 joules. And that is the work function. So that'll be it for this video. Do want to subscribe to the channel and click the bell notification to get notified whenever I drop a new video. God bless you. I'm really exhausted.